Good morning, I am Renu Sharma, Assistant Professor EC Department. Today I am going to start with the next part of Unit 4. Now that is related to PCM, pulse code modulation, pulse width modulation, and PAM. So this is the introduction of PAM, that is pulse amplitude modulation. So in PAM, the amplitude of a carrier consisting of a periodic train of rectangular pulses is varied in proportional to the samples used samples that is collected of a message signal. So basically what we are going to do in PAM, that is pulse amplitude modulation. Let's say this is a signal, that is message signal whose amplitude is which is denoted by xt versus t. Now this is being modulated using a carrier signal. Now this carrier signal is a train of pulses. Now the width of each of the pulses denoted by tau, and this is nothing, this is ct. You can also represent it by pt also. So what we consider, what is the difference between amplitude modulation and this type of pulse amplitude modulation is that which exists in this carrier signal. For the case of amplitude modulation, we have taken a also a continuous time signal, but that is a kind of high frequency signal. It can be a cosine waveform, it can be a sine waveform, but in case of this pulse amplitude modulation, we have considered this kind of train of pulses having width tau. Now this pt can also be represented using the formula, that is summation n is from minus infinity to infinity delta t minus n t, or you can say NTS. What is TS? TS is nothing, it is the sampling time that we have considered, and it is inversely proportional to the frequency of the sample that we have used. So we have to superimpose this information onto this signal. We have to change the amplitude of this signal proportional to the amplitude of this one. So how this our waveform will looks like? First we can make a envelope, then it will be like somewhat like this one. So this will be the case, and you can also draw like so. This is how you can see that the amplitude of this carrier signal is changed proportional to the amplitude of this message signal. So this is the pulse amplitude modulation concept. A PAM is the first step in ADC. What is ADC? ADC is nothing, it is analog to digital converter, and it is the foundation of the PCM. So PCM is pulse code modulation. So in case of pulse code modulation, the input is in the form of bits, that is 1 and 0, and we have to modulate this signal. So the first step is to convert for analog to digital converter is to generate a PAM signal. So PAM takes and analog signal, samples it and generates a series of pulses based on the result of the sampling. So the term sampling means measuring the amplitude of the signal at equal time interval. So this is the concept of PAM. You can see in this waveform also, like this is the analog signal and this is the pulse amplitude modulated signal, and you can easily make an envelope out of this, which will make up this analog signal again. Now this is the PAM, this is the message signal which is analog in nature, this is the train of pulses having width tau, and this is the pulse amplitude modulated signal. Now comes the concept of TDM. So TDM is time division multiplexing. Why we are seeing this topic in between this pulse amplitude modulation or PWM? Because on this basis the PCM will work, that is the main idea behind using this PCM is based on the time division multiplexing. So, an important feature of PAM is conservation of time. So, that is for a given message signal, transmission of the associated PAM engages the communication channel for only a fraction of sampling interval on the periodic basis. So, hence sum of the time interval between the adjacent pulses of the PAM is cleared, that will be for the use by other independent message signals. So, joint utilization of common channel by independent message signals without mutual interference. So, basically what is time division multiplexing in this case? Time division multiplexing case, let us say there are n number of users and these are using a common channel. So, the total time that is available for the purpose of transmission is divided equally among n number of users. So, here are 3. So, the total time is to be divided among 3 different users. Now, 3 different users will going to use a common channel at their specified amount of time. Let us say for first 15 minutes this first user will transmit an information, for the second 15 minutes this user will transmit the information, and this one for the third one case. So, they will going to access the whole channel at their specific amount of time, but the whole channel utilization will be done by the first user. Same in the same manner that will be done for the other users also. So, that is the concept of time division, means the total time that we have is equally divided among n number of users. So, in case of PAM, what is the problem, or you can say what is the condition, that let us say this is how the transmission will be done. So, in between these two samples the channel will be ideal and any other message signal or any other user can use this channel for the purpose of transmission or reception. So, that is the case why we are seeing the concept of this TDM. Now, these are the 3 different types of modulation which is explained in this waveform. Like you can see, like this is the analog signal. Analog signal is the message signal. These has to be multiplied or superimposed on a train of pulses having width tau. So, in case of amplitude modulated pulse, which means this is the case for PAM, pulse amplitude modulation, as you can say the maximum amplitude of the signal lies over here and the minimum amplitude of the signal will be seen over here. So, this is how the amplitude will be increasing and this is how the amplitude will be decreasing. So, this is how we are going to change the amplitude of the pulse of the carrier signal proportional to the amplitude of the message signal. Next comes the PWM. PWM is nothing, it is pulse width modulation. So, in this case wherever the amplitude is higher we have to increase the width of the pulse, and wherever the amplitude is very minimum we have to reduce the width of the pulse accordingly. So, this is how the pulse width modulation will work, like this is how the increasing pulses will be there and this will be the minimum amplitude, this minimum width will be there and this is having the maximum width. Next one is pulse position modulation, that is PPM. So, in case of pulse position modulation you can see that whenever the amplitude is increasing the width of the pulse will shift towards right, and when the amplitude of the analog signal is decreases like here the width of the pulse will shift towards left. So, that is the case how we can design the position modulated waveform. So, PAM, PWM and PPM, in this type the sample waveform has fixed amplitudes and width, whereas the position of each pulse is varied as per the instantaneous value of the analog signal. So, as far as we have seen the amplitude modulation, phase and frequency modulation, in that case any one of the modulation, 2 of the parameters are set fixed and only one parameter will be changed. Like in case of amplitude modulation only the amplitude will change and frequency and phase of the signal will be fixed. So, as in case of this PM, PWM and PPM, amplitude, width and position, in case of this PPM only position will be changed, but the amplitude and width of the pulse will be same. So, PPM signal is further modification of a PWM signal. It has positive thin pulses corresponding to the starting edge of PWM pulse, and negative thin pulses corresponding to the ending edge of a pulse. So, you can see that this is PWM PPM. This is how you can see that a pulse will be drawn with the starting edge of the pulse and the trailing edge of the pulse. So, these two waveforms will be drawn. Negative side will be considered when this will be the amplitude will reduces to comes towards origin, and here when the amplitude is increasing. So, that is why we have used a pulse which is above the origin. So, this is how you can make these pulses. This will be increasing, this will be decreasing, next one this will be increasing, this will be decreasing. So, this is how you can make the pulse. So, PPM is further modification of PWM. This wave can be further amended by eliminating the whole positive narrow pulses. The remaining pulses is called as the clipped PPM. So, whatever we have gained from this PPM waveform, the whole negative part will be remain and the positive part can be removed. Vice versa can also be possible, which will give us the pulse position modulated waveform. Now, next comes the basic elements of a PCM. So, what is PCM? PCM is pulse code modulation. So, that is a kind of digital modulation technique. So, this is divided into three different parts, like first one is the transmitter, second one is transmission path. Now, transmission path is nothing, this is the channel, it can be wired channel, it can be wireless channel, and third one will be the receiver. So, the first case, that is the transmitter, it is divided into several blocks, like first block is the source of continuous time message signal. So, this is the actual source or the source which will going to generate the information that you want to transmit, that you want to modulate with the use of this pulse code modulation. So, it can be, it is basically a kind of analog information, it can be your voice signal, it can be a text message or any kind of signal we can consider. So, first we have to pass it through a low pass filter, so that it will going to restrict the signal in a specified range of frequency. You can say from 0 to Fs is there. So, that will be considered as a cutoff frequency. So, outside this range the signal is considered as continuously varying signal, you can see, you can say, or if I am going to modulate a kind of continuous time signal, speech signal, and I want to do some processing on it. So, it is a continuously varying signal. So, when a processing has to be done, so we have to consider a portion of the signal which is stationary in that time limit or in that frequency range. So, that is the use of this low pass filter, which will going to, which will extract a part of the signal which is considered as stationary in that range. Now, that will be passed through a sampler. So, sampler will basically convert the continuous time, continuous amplitude signal into discrete time continuously varying signal. So, that is the first step of ADC, that is analog to digital converter. So, these three steps are basically included in a ADC, that is analog to digital converter. Now, next part will be the quantizer. So, quantizer will convert the continuous amplitude into discrete amplitude. So, this will be a discrete amplitude and discrete in time signal. Output of this will be an encoder. So, encoder will going to encode the dynamic range of the signal that will be extracted from this particular type of amplitude variation. So, that dynamic range, let us say we have considered 2-bit encoder. So, it will be 0001 1011, and if it is a 3-bit encoder, let us say V is equals to 3. So, it will be 000 to 111. So, that is how we can divide the dynamic range. So, PCM signal applied to channel input, from here this will be applied to the channel input. So, this is the part of the channel is there, that is transmission path. So, since it has to travel over a channel, so it will be affected with noise, because most of the signal in case of this communication, it is affected with noise at the channel only. There are very less amount of internal noise that will be due to the components that we have used in designing the different devices like resistance, capacitance, inductance, BJT, or some other devices that we have used in designing a particular kind of device. So, that also produce some kind of noise due to the motion of the electrons and due to some other constraints. So, that is considered as internal noise, but the major noise that will going to affect the signal quality will be done at the channel. So, we require regenerative repeaters to remove such kind of noise which will going to degrade the quality of the signal if it is not used. So, distorted PCM signal produced at the channel output, it will be passed through a regenerative repeater. So, it is totally your choice that how many numbers of regenerative repeaters you require. It can be 2, it can be 4, depending on the distance between the two repeaters and depending on the distance between the transmitter and the receiver. Let us say it is 50 kilometers. So, practically to install regenerative repeaters, it is after 50 kilometers due to the curvature of the earth. But if you want to increase the quality of the signal, you can also use it after every 10 kilometers. So, 4 to 5 different regenerative repeaters are required at every 5 kilometer of distance. So, that is the case of transmission path. Now, after this, the PCM that we have received at the receiver input will be of good quality, that has no noise component present in that signal. So, the final channel output will be there, then this is a regeneration circuit. So, whatever remaining noise is there, it can be removed by using this regeneration circuit, then it will be passed through a decoder. Now, after this decoder, there will be a reconstruction filter. Now, reconstruction filter is again a low pass filter that will going to filter out the higher frequency terms that will be present after the purpose of decoding. Then higher frequency terms will be removed and then we can easily demodulate or we can easily send the signal with a good quality at the receiver end. So, these are the basic elements of a PCM. Now, next is in PCM, the message is represented in the form of coded pulses by representing in discrete time and discrete amplitude. So, this is the case, like this is the binary data. Now, this will be the amplitude 0, this will be amplitude A. So, for 0, if we are using any kind of line coding, so for 0 bit we are transmitting 0, for 1 bit we are transmitting an amplitude that is equivalent to A. Now, A can take any value, it can be 5 volt, it can be 6 volt or any value that for the system you have designed, and the bit duration that is considered is known as denoted by TB, that is the time required for a single bit transmission. It can be 0, it can be 1. So, you can say that this is also TB, now this will also be TB. So, this is the TB bit duration that we have seen. So, sampling is done with a train of narrow rectangular pulses to ensure perfect reconstruction of the message at the receiver. The sampling rate should satisfy the Nyquist rate also. So, what is Nyquist rate? Nyquist rate means sampling frequency should always be greater than equals to 2 FM, that is the maximum frequency component that is present in the message signal. We have to multiply it by 2 and it should always be less than equals to sampling frequency. So, that if we consider this Nyquist rate, so whatever signal that is reconstructed after the purpose of interpolation, then the signal quality is much better. So, a low pass filter which acts as anti-aliasing filter is used at the front end of the sampler, which removes frequencies greater than W hertz. So, the signal after sampling is discrete in time. So, that is the case for sampling. Now, next step is quantization. So, as you can see that after quantization, the signal will be in the form of staircase. This is known as staircase approximation. Whatever signal that we have considered at the output of the sampler, it will be converted into a staircase kind of approximation using this quantization step. So, conversion of analog samples into digital form is known as quantization process, and the transfer characteristics of this will look like a staircase appearance. Amplitude quantizing is known as mapping samples of a continuous amplitude waveform to a finite set of amplitudes. Now, you can see like this is divided into a number of samples. This is known as basically step size. So, the step size can be variable, it can be fixed also. So, there are two types of quantizer that are present, it is uniform and non-uniform. In case of uniform, it is the step size is fixed at every quantization step, but in case of non-uniform, the step size is varying in nature, that is delta. So, that is the two types, like first one is uniform, that is mid read and mid riser. So, how we are going to draw this waveform? Let us say if we consider a pulse whose reading edge is this one and rising edge is this one, this is the rising edge and this is the reading edge. So, in case of this mid to read, what we the waveform will look like somewhat this. So, the origin will be there at the in between the reading edge, but when we are talking about mid riser, then this is how the pulse will be there, like it will be at the between the rising edge of the pulse. So, this is how we are going to draw, and you can see that the delta will be fixed in every case. Next one is the non-uniform quantization. So, in case of non-uniform quantization, the delta will be varying and it is of two types, that is A law and mu law. So, that is the case for quantization. Now, this is a very good example which is showing all the steps in detail, like you can see. This is a message signal xt which you want to transmit using the PCM concept. Then these are the quantization level. Now, you can see the dynamic range will vary from minus 3.5 to plus 3.5 value. So, we have to consider the encoder bits depending on the dynamic range. So, that is let us say there are 8 number of levels. So, it is very much accurate that we can use 3 bit, v is equals to 3 bit. So, 2 to the power 3, there are 8 number of amplitude levels that will exist. So, that will make up a code number. So, this is the natural sample value, like these are the exact value. Now, when it is rounded off to these levels that we have set, so that will be the quantized sample value. Now, next these are the code numbers that we have seen. So, these are converted using the different types of PCM sequences, like 5 can be encoded using this 101. This is just a binary representation of the decimal bits. Decimal digit, that is 7 can be represented is represented using 111. So, this is how this is the PCM sequence. Now, next is PCM transmitting end. So, this is how this is the transmitter, then band pass filter, sampling, quantization, encoding. So, this is the PAM signal that you can make. PAM signal is nothing, this is the amplitude that are collected at equal time instants. These are the quantization, this is encoding. Now, encoding is basically when we have considered 3 bits of encoding. So, this is how the waveform will be plotted, the coded bits. Next is quantization process. So, quantization process is peak to peak average of the input is subdivided into different types of decision levels that we have already seen. So, it is just dividing into equal number of steps. This is the quantizing process that we have already seen, the two different types of waveforms, that is mid read and mid riser. Now, this is the formula that has been showing the number of levels. So, since let us say there are 8 levels are there, that is the dynamic range is divided into 8 equal levels. So, it will be denoted by this formula that is 2x max divided by delta, where delta is the step size and x max is the maximum amplitude as the positive or the negative side. These are the two waveforms for mid read and mid riser. Last one is the encoding. So, to make the transmitted signal more robust to noise, we are going to encode the signal using n bit encoder. This is the electrical representation of the binary data. This is all about today's lecture. Thank you.